here we go. All right, so first off, it's on the bottom of the screen, but probably the most important thing, you guys have winter break, essentially starting tomorrow, unless on your 8th grade schedule. Okay, so not really starting tomorrow. If you have work to do, and if you need to utilize AO, you're going to do work tomorrow. Aside from that, if you're all caught up and you don't really have any work to do, it's winter break. Excuse me. So hopefully you guys get a chance to recharge over break. We do have Khan Academy work due tomorrow. I think most of us actually aren't done with that, so I'm assuming you're going to get it done today after we talk. And today what we're talking about is similar triangles. So first off, before we jump into the triangle work, let's take a step back. And this stuff is also due today, or due tomorrow, sorry. But did anybody have any questions from the similarity and transformations exercise, which part of what we did yesterday, right? It's easier for me to just say yesterday. Part of what we did yesterday was talk about like similarity and congruence through that Desmos activity. So when we look at EJGK compared to the original EFGH, who can tell me what's up here? What's wrong? Like, are these similar figures? Are these congruent figures? Are they neither? Do we really need to review some vocab, probably. Guys, I'm going to do a lot of like random today because I got a bunch of questions through the slides. So if you know this one, it would behoove you to engage right now before I randomly ask you one that you might not. So is the pink and blue dashed quadrilateral congruent or similar or neither to the solid blue quadrilateral? Sorry, I'm getting kind of washed out with the light behind me. My background is so boring now. Ellie, what are you thinking?
He used a vertical stretch, so the quadrilaterals aren't similar.
Yeah, so remember, just like when we're changing graphs, like our quadratics, or sorry, our parabolas or things like that, if you just do a vertical stretch or compression or just a horizontal stretch or compression, it's not similar to the original shape. And to be congruent, you would have to be similar and equal, right? So we're going to define those and write those words down again here in a second once we start taking notes. But again, kind of a soft start while we try to make sure we get everyone into class. What about this one here? So it says Bastion, which I love when they use the name Bastion because that's what we call our dog, Sebastian. But Bastion was able to map quadrilateral OPQR onto ONML, careful with the order there, using a reflection and a dilation. Sebastian said, I was able to map the quadrilateral using a sequence of rigid transformations and dilations, so the figures are similar. Anyone want to talk to this? Not Ellie. Avi? What's the difference? It is, actually I should ask, is a dilation a rigid transformation? And if your answer is no, why?
No, because the size of the stick is changing.
Yeah, rigid preserves size. So guys, let's go ahead and head our notes, similarity and congruence. I'm kind of giving up on us. And it's up here, by the way, similarity. And I think... here it is, if you want to see it written out again. Similarity and congruence. So, as a reminder then, popping back to Bastion's question, and guys, I should be able to see when you're taking notes by like you look down, you look up, you look down. So similarity and congruence is what we're going to head our notes with today. And the first thing we want to remember is rigid, not just the tool brand. Rigid means we preserve the size. So rigid transformations, that's why they call them rigid, right? So for example, hey Amar, are you writing this down? Because I see you real close to your computer, but I don't necessarily see you writing the notes. Do you need me to get closer to it? Are you having trouble seeing? Hey, Amar, mute your camera. I don't think you have enough internet. Mute your camera so your internet is easier. There you go. So, for example, what are rigid transformations? What did we talk about in that activity in Desmos? What's
reflection, translation, and rotation?
Yeah, so a reflection keeps size, a translation, which people also call slides. Reflection, translation. You also said rotation. And then in that activity, I don't know if I would say we learned, but we reviewed, right? We practiced what dilations do. What's a dilation? And can anyone tell me when it's happened to you in real life? Anyone ever been to the eye doctor? Yeah, so you said it at the same time as me. Your eye doctor, right? Your eye doctor puts drops in and it dilates your pupils. So dilation, who can define this for me? How can we define dilation? We know it changes size, but how? What does it use?
Uses a ratio.
Yeah, what's the name of that ratio? There's a formal name.
Scale factor.
Yes, so it uses a scale factor to change size proportionally, right? The whole shape is going to change size proportionally. I think it's A-L-L-Y, but I could be wrong. I need to pull this up just a little bit. So if Bastion did only use rigid transformations and a dilation, then our result is similar, because similar shapes, as we've learned, how could we define similar shapes?
The shape doesn't change, but the size can change.
What do you mean the shape doesn't? So a triangle is similar to a triangle?
Oh no, like the entire, not just like the shapes, but.
So you're right, different size, right? So for similar, go ahead and write down different size. But different size, but all sides. Ooh, so yeah, different size, same angles. And the sides are proportional, right? So we could actually just kind of draw an arrow up. So our sides are going to, proportional tells us there's a common, exactly what I think it was Kaylin said, there's a common ratio. So this is where and why we end up with problems like this. So now, I understand when these were thrown at you, you might have just said, oh, it's algebra. And you're right. But the reason we have you practicing this algebra is so that we can deal with similar shapes. So I was going to review the first one, and I wasn't planning on doing the second or the third one here unless we need to, unless somebody has questions. But just to review and make sure we're comfortable on how to do these problems, this would be like from shape A and shape B, right? That sets up a ratio that any side that corresponds from A to B will share a common ratio. So maybe the side on A was told to us to be 2y minus 4, and the side on shape B is said to be y plus 7. We compare that to another pair of sides that match each other, And maybe those sides are actually 1 compared to 3. And guys, we're going to see this later in the lesson. We're going to practice this. So what do we do when we have a fraction equal to a fraction?
Cross multiply.
Yes, we cross multiply. So 3 times 2y minus 4 equals y plus 7, because times 1 doesn't do anything. 8y minus 12 after the distribution equals y plus 7. We need to sort, right? Get like terms with each other on the same side. Easiest thing to do is look for the biggest variable value. Keep the variable on that side. Sorry, so not negative 8y, but negative y. Just negative y, or just minus y, right? These make 0. If you can keep your steps straight, you can do both at the same time. If we took the constant off of this side, we want to take the, if we took the variable off of this side, we want to take the constant off of this side.
Wait, I think you messed up.
Did I? I do that a lot. Oh, 6y, isn't it?
2y is 6y.
Yeah. That's, sorry, my brain did the 2 and the 4 and got 8. Because I'm silly. That's a 6. It's not a very pretty 6. But we'll fix that by saying this side is 5y. Thank you for the catch. Good work. If you were here, I'd give you a piece of candy, because that was a legit math mistake. 7 plus 12, assuming my math is right. 19. I think. Somebody tell me if I've made another mistake. But then we could say, well, the value of y must be 19/5. Any questions on how we solve any problem like that? Now, what I thought was interesting about the order that Khan Academy paces this stuff in, and I know why they did it, because they want you just to like remember, oh, this is just algebra, is where we apply this is in stuff that we haven't done yet. Now, before we move on to that, we're going to make sure that we know the difference between similarity and congruence. So, similarity versus congruence, their symbols are what we want to make sure that we recognize for how we write the statements. So let's say that we have this doesn't work up here very well. Let's say we've got a shape where ABC is similar to DEF. How do we write that mathematically? What symbol do we put in the middle? What's it look like? And I think this is something Khan hasn't done with us yet.
Is it the equation with like the squiggly line on top of it?
Anybody else have guesses? I'm not going to answer that till we hear if anybody else has guesses.
And wouldn't congruent just be an equal sign?
You're close. You're partly right. What does the equal sign mean? The exact same thing. What does the squiggly line mean? Yeah, what do we use? Don't write this in your notes. I'm just like off to the side. What do we use the squiggly equals for? Amar? Amar, your hand's up. Go ahead and unmute and talk if you want, man.
Okay, I just realized I did this in Khan
some reason I just forgot, but I think I know how to do this though.
What do you mean?
Put the you already never mind.
I'm curious if you might be lagging. Yeah, we already solved this one, but what we're asking now is what symbol do we use for similar? Do you know that, Amar?
No, I haven't been that far in Khan Academy yet.
I don't even think this is in Khan Academy. This is just me teaching you guys. Similar is the squiggly. Congruent, well, sorry, I kind of jumped over. What do we use this for? If I said x is squiggly equals 2, 5.
Well, obviously, estimation.
Yeah, like approximate, right? For like estimate. I don't really like the word estimation because estimation is like, hey, estimate how much I weigh. It's like a guess, but approximation is where we round, right? So be careful. Estimation and approximation are kind of different words. I know we kind of let you guys use them the same, but mathematically they're kind of different. So guys, if you were to look up like similarity symbol, what's funny is the first thing that popped up, because I was curious if any of you guys were Googling it right now, what you would see. The first thing that pops up is the congruent symbol, and of course it depends on your search results. The congruent symbol is equal and similar. So it's the equal symbol and the similar symbol. Whereas similar is just the single squiggly line, because they're not equal. They're not even approximately equal. They're similar. So this is weird compared to our squiggly equal sign where we use it for like an approximation. This means there's a common ratio. So you might want to make the note that this symbol is really, it's telling us similar, but it's also essentially telling us there's a common ratio. So this tells us common ratio. And this tells us that that common ratio is 1. They're equal. Sorry, that's a bad 1. Ugly. And why did I put an N? Guys, I'm trying to do too many things at once. This says common ratio. This says the common ratio is 1. Sorry, I think my brain was stuck on the word common when I wrote the word ratio, and I went ahead and put an N out there. That does not belong there. Math teachers can't spell. I can't even word. What am I talking about? So, now that we know our symbols, here's the funny thing. Khan Academy doesn't seem to use those very much. But if you are told this shape is similar to this shape, or this shape is congruent to this shape, guys, I'm going to switch back to a Sharpie for this, like big fat Sharpie. This needs to be in your notes. What do I mean with order matters? Where'd my blue go?
Order of the letters matters when you're like writing a congruent statement or a similar statement.
Give me more. Why does it matter? What do we then do with it? So if I say A, B, C is similar to D, E, F.
Because then you can know that the line AB and DE have a common ratio.
Ooh. So you said A, B, D, E have a common rate. So we can set up the first 2 points, or the side, the first side.
Excuse this interruption.
This doesn't happen often.
Damien to the remote office, please. Damien to the remote office.
The first side over the first side. The second side, B to C. And guys, these are easy because we're using letters that are in order, but often they're not nice letters that are in order. So our second side, BC, would correspond with our quote-unquote second side, What's our second side over here? Just shout it out. I see hands. Yeah, EF. And this is where people goof it up. CA from the last point back to the first point will be over FD. So the order matters because it lets us set up those common ratios. And the common ratios are all going to be equivalent. Now, if it's also congruent, now this is where if you have colors, then these all equal 1. If, right? Big ol' if they're not just similar, but they're also congruent, all of those common ratios would equal 1. Otherwise, they just equal each other. Any questions on what we've written down so far? Getting us to the quote-unquote end of the first page for me. All right, that took longer than I thought, but it's my fault. All right, so check this out. When we start to talk about similarity, we first have to know how do we determine similarity. So I'm flipping pages here. If you're not flipping pages, I would draw a squiggly line across and label it determining similarity. Or you could just even say similarity like question mark. Ooh, does anybody have a guess? And I have this question on a slide after this. Anyone have a guess of why we're using triangles? Why not quadrilaterals or pentagons? But like, why triangles? There's really like 2 reasons. Oh, there's probably more than that, but. Kaylin, your hand went halfway up.
Maybe because you can, like, all the angles add up to 180, so if you have 2, you can tell the third.
Ooh, okay. Yeah, that's true in like every shape though, right? So if we have a quadrilateral and we have 3 of the angles, we know the 4th one. So you're right, but that also holds true for other shapes. Avi? Then L?
Is it because of like angle side angle?
Well, that's in here. We're going to write that down here in a second, but what do you mean?
Like, you can tell if they're similar by using them.
Is angle side angle? So I see angle side angle up on the screen, but I also might see side angle side. So is that why we're using I mean, triangles have theorems that go with them. Guys, I know a lot of you didn't have me for math last year, but a mantra that I go back to all the time is I'm here to make your life easier, and that's actually mathematics is here to make our lives easier, right? A triangle is the easiest shape we have, right? It's got the least amount of sides possible, aside from a circle, which we won't even go into that. It's got the least amount of sides possible. It's got the lowest angle sum measure, right? Like Kaylin said, the angle sum measure is 180 degrees. And here's the kicker. First, I have to write down Y triangle. Every shape, and now somebody might be able to finish my sentence. Every shape when we say every polygon. So polygon has to have straight sides, right? So every shape that has straight sides, straight edges. Sorry, we should start to say edges because sides is a bad word. Edges, God, I have no shapes. I have nothing because everything's packed up. An edge is like an edge, right? A face is the flat face of something. A side, what's a side? A side is like mashed potatoes, right? So side is a word we're going to start to try to not use. It's edges and faces, okay? Edges and faces. So every shape, polygons, they have straight edges, can be subdivided to triangles. every shape we work with, every polygon we work with can be subdivided into triangles. So literally everything we have is a bunch of triangles. That's it. We're always working with a bunch of triangles. Sorry to tell you, the whole world is just triangles. Triangles are extremely strong too. Start to pay attention to where you see triangles in architecture. It's pretty crazy. So here, they give us 2 pairs of angles and 2 pairs of sides. Now, I want to go back to something I think it was Avi said. If we know 2 angles, I'm going to make like an if column over here. If we know 2 angles, and guys, we're going to start to use some shorthand. This is the symbol for angles. Technically, that's the symbol for the measure of an angle because the arc across it. So guys, if we want to be technical, this means angle. M of angle means the measure of the angle. Another way we write that is that, an angle symbol with an arc across it. Now this means less than. Angle should have a flat bottom. I know I'm taking like a moment for stuff that is boring, but the symbol we use for angle should have a flat bottom and then arc up. The reason for this, and this is way further than what you care right now, but the reason for that symbol is when we talk about our unit circle, all angles start right here. So when angles start in the unit circle, they start flat. They start pointing out what is like our x-axis. We'll talk about the unit circle later in the year, but this is kind of where this is derived from. So if we know 2 angles, then what do we actually, if we know 2 angles, what did Avi say? I think it was Avi. If we know 2 angles,
Then we know the other
yeah,
left angle.
yeah, we know the third. If we know 2 angles, we really know all of them. So one similarity proof we're allowed to use. I'm going to halfway down my paper. Triangle is angle, angle, angle. And to use angle, 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 all we have to do is know 2 angles. So technically, here's the fun thing about math trying to make your life easier. Angle, angle, angle is actually just angle, angle. We don't need the third A. So this is not triple A, right? It's actually angle, angle. Because if we know 2 angles, we actually know the third. So great. So if we know 2 sides, do we know the third side? Oh, well, that's not as convenient. We know something about the third side, right? If we think back to our triangle inequality theorem, the third side of a triangle, right? I packed those things up yesterday. There's a certain range that it can exist in, right? The side can be no longer than the sum of the 2 sides, and it can be no shorter than the difference between the 2 sides. So remember, if we think about our triangle inequality theorem, we've got a range that our third side could exist in. Man. What if we know 1 side, 1 angle? 1 side, 1 angle. How convenient would that be? So here, we know 2 angles, 2 sides. We really know the third angle. We said angle, angle similarity can work here. So, on questions like this where we see A, B, C primes, by the way, if this does not jump out in your head as prime notation, I've got a note about this in a slide or two. because we know two angles are congruent to each other, we actually know the third angle is congruent to each other. And since the sides are also congruent, it pushes us from similar to actually being congruent. So two pairs of angles and a side. So if we know two angles, I'm going to write this down, two angles and one side. Who can help me out here? Does this work? Can we solve these? Could that 18 be anywhere? So what if the 18's between G and H over here, right? G and H prime, but then it was between L and J over here. So what theorem is this? Who's already done their work that can tell me what matters here if we know two angles and a pair of sides? We wrote it down on the last page. What matters?
The order.
The order. So if you're given two angles and a side, what they're showing us here is angle, side, angle. So we have an angle with an included side. What this means is the side is included between the angles. Now, what if the side isn't included between the angles and it was actually angle, angle, side? I forget if I put one of these examples in here. I did not. So I knew I wanted to cover too much today. So angle, angle, side also works. Because really, remember, angle, angle, any angle, angle really knows all three angles. So as long as the order matches, so you have to check the order of the angle to the side. They have to be the same. So if it's like one arc, then two arcs, and then your side, like we have to check the order. So our alert for angle, angle, side is just check the order. Now what if we had one angle and then two sides given? Uh-oh. I'm gonna get in trouble. Guys, I'm scared now. My mom might walk in here with a bar of soap. So I wrote down side, angle, side, but in a different order. I wrote down angle, side, side, and I'm afraid to actually, I'm just gonna, it's not, this doesn't work. No joke. Not only is it a bad word, I've got periods. It's obviously abbreviating for something else. Not only is it a bad word, but this just does not work. It does not show similarity because we only have one angle and it's not between the sides that we know. So this does not work for similarity because the side or the angle is not included. Side, angle, side does work. Side, angle, side does work when the angle is included. I'm going to put that in all capital letters too. When the angle is included, it does work. So this is one of the biggest things I wanted to tell you today is that angle, side, side does not work. And you'll see some examples when you can relate the triangles through angle side side, and it does not work. I have a typo here. So check out this one. Take a moment. If we were asked to write the similarity statement here, we have a shared angle, right? So the shared angle is always going to be congruent to itself, like an angle is congruent to itself. What's the order? Take a moment, try to write this order on your paper. What is the order? Sorry, I'll move this a little bit because I know my recording button thing is in the way. So it's not as easy as saying ABC similar to A prime, B prime, C prime, right? That'd be too easy. Notice that I have careful in all capital letters up there. Lamar, are you still there doing all right?
Yeah.
If these shapes are similar, what should we be able to check for? Katie Ann, what do all similar shapes have that we could check for? Okay, and we don't really have any angles given to us here, so all we really have to work with is sides. So similar, so what does similar sides mean? What math is created from similar sides?
Division.
Yeah, if I flip back in my notes, what did we say similar shapes have? Their sides all have
A scale factor.
a scale factor, a common ratio, right? So if I set up triangle ABC, well, let's check. 4 extends to what? Wait, what?
Get the order right.
Wait. Katie Ann, what?
It's not matching up, so you really have to kind of flip it. So really, AC will be the same as AB.
So what I need you guys to be able to do is recognize this without me saying careful in all capital letters. Katie Ann, you're absolutely right. This is not lining up. If your eyes did not catch immediately, this is the longer side of the triangle of the legs that were given. And this is the longer side of the legs that were given. So if we look at the big triangle, ADE or AED, whichever side, like whichever order you want to go in, the 8 compared to the 6, the 8 is your longer side. So what Katie Ann is saying is AC matches up to AD. So we can say AD or AC goes to AD. So I need to show my notes here. AC goes to AD. AC was 4. AD is 8. So we're thinking the ratio would be 2, right? Like a scale factor of 2. And then if we write ABC similar to, well, if AC, AD, so D, well, so this has to be E then, right? We have to have the other point in the middle. So if you were asked to write this similarity statement, it's ABC similar to AED because the order got kind of weird. We always have to check for which one is the shorter leg compared to the longer leg. So then 3, AB, 3, becomes 6, right? And that checks out. It has the same common ratio. Does that make sense? Do I need to explain it another way? So now we start to see triangle proofs. And this is why you're all going to love me in January when we come back, when we start writing proofs together. But luckily, and you won't care about this right now, but I'm being straight up honest with you guys. You will appreciate that I let us jump right to 2-column proof as opposed to flowchart proofs. We will learn both. We'll talk about flowchart proofs, but if you did any of those in Math 1, I'm not quite sure about Mr. Hall's class versus the summer school class. Flowchart proofs are kind of annoying, at least in my opinion, because it's like bubble, line, bubble, like it's meh. It's the organization is not great for a math brain. This is what we call a 2-column proof. We have a column for the statements and a column for the reasons. I know I'm running out of time. That's why I'm talking quickly. We're going to pick this back up in January. So when we look at what Raphael tried to do with ABC to ACD here, what is the first mistake that he made? So let's scan through his proof. He said side AC to AD. AC to AD. So notice how AC could be part of either triangle. AC is part of the big triangle and it's part of the smaller triangle. Okay, so that'd be like long side to short side. I'm not quite sure about the length of this side. AB to AC is also 2 to 1. So then they do AC over AD, AB over AC. Guys, is everything that he's said true? Like, is that ratio 2 to 1? Is this ratio 2 to 1? Margaret, what do you think? Told you guys I was just going to call on people kind of randomly today. Is 8 to 4 2? And is 4 to 2 2? Like, are those common ratios 2? You're muted, by the way. Is this enough information to prove similarity? No. Guys, all he's done is relate 2 common ratio sides. That's not enough. If we've been told that this is similar, I told you these shapes are similar, write a statement. But we don't know that these triangles are similar. Side is not enough to prove similarity. He either needs what? What 2 things could he have here to help him out? You either need an angle between the sides, or the third side. Thank you. So please, in your notes, if we have side, sorry, I'm going to go back and use a weird part of my notes, but if we know 2 sides, oh, and I had this up here actually, sorry. If we know 2 sides, we either need an included angle, or the third side. Because guys, if we go back to what we had written down, if we can prove this, sorry, too many pages of notes. If we can prove this, forget about the equal to 1. If we can prove the common ratios, we prove similarity. But if you only have 2 sides, that's not good enough. 2 sides either need an included angle or the third side. And really we're out of time. So because I've already assigned some stuff to you guys, I think I assigned stuff that's due like after winter break potentially, or if not, I'm going to. So if you're bored over winter break, you have stuff to do. But I'm going to make it due like when we come back, after we come back. But what we start to do here is very carefully, and I'm going to do one that we can see more of, figure out what sides match each other by using the common ratio. So when you're told that the triangles are similar, you know that there is a common ratio. So we have to set it up to match appropriately. If I do 28 compared to 5, and then 10 compared to 14, that's wrong, right? We can probably see pretty easily that that would be wrong. also, the order they give it to us in should tell us what sides match. So by them saying A, B, C is similar to J, K, L, A, B should match your J, K because order matters. So A, B being 28 would match my J, K being 14, and our scale factor here would be either 1/2 or 2, depending on which way you're going, right? That common ratio scale factor. So then we can use that to solve for Q. Likewise, as they get harder, XY, okay, XY is kind of annoying. And to AB, crap, they didn't even give me AB. So if I can't use XY to AB, move on. What about YZ? Okay, YZ is 3. What would YZ match with? Gotta unmute and tell me. What would YZ match with?
BC.
Yeah, BC, which then tells us the scale factor here is 3. Thank you, Kaylin. All right, guys. I know I'm over the time I normally try to stick with, so I'm just going to say that we made it to here today. We will pick, obviously you guys can see I had a ton more set up. We end up getting to situations like this, where we're able to actually solve for the unknown sides that are partial pieces of the total side. This is where we're going to go back to the stuff that I told you we just practiced it just doing algebra. Those advanced solving for missing pieces, that's where we're going to set up those proportions that look kind of funky and use binomials. That's where we're going to do that sort of algebra. So it's 10:50. I want to make sure that you guys have time for a break before your next class. So we're going to wrap right here. Yeah, please use AO and extensions over the next couple days to try to get as much wrapped up before winter break as you can. And hopefully you guys have some downtime and can enjoy break. So happy holidays, whatever you celebrate. Hopefully it goes well. Be careful if you're putting any fires in fireplaces. Careful, fire will burn you. Leave some cookies out or some carrots out or whatever you leave out. All right, happy holidays, guys. Have a great break. Bye.